Okay, so let's look at the web page and make sure everybody's cool with what's going on. Let's look there, here. See, I got next semester's courses up there. Also, what I'm hoping to cover in the following lectures. Notice this coming Monday, a week from today, and 2 weeks from today, 10th and 3rd of November, no office hours or lectures. We'll have another makeup lecture on Friday, which will be discussing the course projects. In the meantime, I want to point you to a few things. On the LT Spice, I went ahead, so you can get ahead and start looking at this. Let's pull up MATLAB. And so someone's peeking in the windows back there. No, you're not getting this classroom. Okay, so if you look here, on this computer, you won't get them when you download it, but I already have the raw files for the simulation. So if you take like this figure 933 and you look at it, you'll see K delta 1 sigma, that's 8 path, and you'll see a clock generator, and we went through this already a little bit. On the output, the way you do the clock phasing is somewhat arbitrary. I just tried to maximize the timing margin so that when like Q1 was switching, then V1 underscore 1 wasn't. So if Q1 switches because of Q1 underscore, if they switch at the same time, then you'll clock the right value and you have one whole clock period for it to make a decision. Okay, so you have to play around with this, but if you don't know digital design and you don't understand how to clock a flip-flop, this is going to be a problem because you are clocking your comparator here and the D latch at the same time. Well, it's going to grab the previous value. Okay, so you have to make sure you understand what's happening there, because if you clock it slightly after and this guy's not making full logic, you'll make mistakes. Does everybody follow that? So if I clock them at the same time, this value is sitting there all set up, it captures, and then this one makes another decision and has a whole clock period to make the decision before I clock it in again. Anyway, we'll cover this stuff in more detail, but the digital part, just pretty much common sense. What's that? No, it's if you clock them at the same time, it's not going. There's a delay through here, right? So the output's not going to change until after the delay. However, you're capturing the previous value, which means you have a whole clock period for the output to settle. So you're not going to make digital mistakes. Now, you want the delay feeding back to be fast, but that has nothing to do with capturing the digital data and getting it into MATLAB. Does that make sense? So because there's a delay, you can clock these at the same time, and it'll capture what the previous value is. I mean, this is common digital stuff. I mean, there's nothing fancy here, but I was doing, yeah, if it was an ideal comparator, there's no delay, and this was changing, and the clock edge starts going high, and this starts changing exactly the same time as this, I mean, then this is moving. But if you look at the edges, then you're going to see that, oh, this edge and this edge, there's a delay, and then this one has one whole clock period to settle before I clock it in again, the rising edge. Of course, after today, I taught digital logic, like ones and zeros, and doing some simple gates in my 421, 621 class, and scared the hell out of me. So I'm saying, oh, this is easy, but if it's not easy, you got to tell me. A couple other things. In order to avoid having huge raw files, if you look at the sims, I use the .save. So if I said, oh, I already have the simulation data, which I do, and I wanted to show those clocks, well, they aren't not listed in my .save because I've got hundreds of signals. I don't want to save all of them because I end up with a big file, so it'll slow things down. So you'd have to put what you want to save in the list here. It's not like normal where we don't put .saves, and so it saves everything. Okay. Now I also went here, and again, I'm just doing this so you can play around before we talk about it on Friday. But I also went to the control panel, and I think I mentioned this last Friday, and I said delete raw files and ask first. And so when I close this, it says, do you want to delete the data file? If you say yes, it deletes the raw file and you can't run the MATLAB script. Okay, so I'm going to say no. Then I'll go over here and then I'll navigate to the desktop, open the Chapter 9, and again, you're not going to have any of this stuff if you didn't download it since I emailed you on Saturday or whenever it was, okay? Because I spent all that time up drafting those schematics. So you could look at them and modify, all right? So you go, which one did I open? Was it this one, I think? And then you say, okay, the MATLAB scripts, we can go through here and explain what everything is, but you know, in the meantime, read Chapter 9, know what k-path is, that's the number of feedback paths, know what your oversampling ratio is, because you can crank that up and it chokes off the bandwidth, you just filter more. And power supply, if you use a 1-volt supply, you got to change this and all that. You hit go, change the folder. And then I've got all these plots here that pull up, and you can see, like, and I want to just show you. So this is reading the data out in the serial mode. So you know you're clocking the data out in parallel. But once you get into MATLAB or you have it in a serial, you can do DSP and you can treat it as if it's coming out at the real high-speed rate. Okay? So even though you clock the data in one big word, it's sequential. You can treat it so it's coming out at rate of 1830 megahertz, which is roughly 500 picoseconds. So your data is coming out effectively at 500 picoseconds, but you're letting it settle, then you're capturing things all together so that things are in parallel. So once it's digital and you have it in a serial word, then you can see what's happening, all right? Does anybody follow that? Nobody follows that, so let me talk about that. Because again, I'm not going to be able on Friday to say, okay, here's the projects, this is what's going on, and then you go, oh, okay, and it make total sense. So let me make sure I'm recording, because one of my students today asked me some question about addition and subtraction and 2's complement, and I started to explain to him and said, would you mind waiting till you're in class so it can be recorded? And I'm like, does that mean that I'm not clear? No, I just need to go over it a few times. I'm like, all right. Okay, so let's just pick some data, right? So here's one data bit, it comes out, and then it waits, and then let's say it's just alternating ones and zeros, all right? So let's say this time here was, I'll just use 100 megahertz. So this time's 10 nanoseconds. So if the next clock phase comes out, and it's going to be delayed by 1.25 nanoseconds, this is a little slower than that example in the ring oscillator that you saw. Then this time delay here is 1.25 nanoseconds, and the rate it comes out, the effective sampling rate is 800 megahertz. So here I've got a 1, here I've got a 1, right? So in real data, there's problems with decisions. So instead of clocking this 1 in immediately right here, I'm going to wait till the next rising edge and clock the 1 in here. Okay? When I do that, I wait for this rising edge, clock the 1 in there. I get it in the flip-flops at different times. Let's just do 2. And then I clock them out in parallel. So in this, I got a 1 and a 1. Okay, if I think of serial, then I know that, hey, effectively, my data stream is 1, that's 1.25 nanoseconds in width, followed by another 1 that's 1.25 nanoseconds, even though the data is coming out at 100 megahertz in slow, big words. So if I look at the data coming out, it's 1, 1, it's a word of 1, 1, whatever the next words are, but then I treat it in the MATLAB like it's serial, like it's a serial bit stream that's at 800 megahertz. This is a 1, then that's a 1, and if the next one was a 0, then the next one would be 0, so I have 1, 1, 0, 1.25 nanoseconds later, etc. Does everybody follow that? Okay, so let me repeat myself one more time. I don't mean to bore you. Okay, what I'm doing, each path is outputting data at 100 megahertz. I'm saving it at a slower rate. I'm saving a word, say 4 bits at a time. That means I'm saving it after I get 4 bits in. I save those 4 bits, so it gives me more time for the digital data to set up before I clock it and save it. Then I read that out with MATLAB, so I read a word out in parallel. So even though the bits are individually changing at very fast rates, the word I read out is slow. It's 4 times slower or 8 times slower, whatever it is, all right? But I know the bits are like serial. So I know it's faster rate. So let me give you one more example. Let's say that I have this string right here, right? And I go into a shift register. Okay, and let's just say I clock in 8 bits. And each bit's width is 5 nanoseconds. After I've stored the 8 bits in the shift register, after 40 nanoseconds, I chunk out the 40 nanosecond, I chunk out the 8-bit word. Does everybody see that? Okay, I look at the word, whatever it is, 11011000, 0. And even though the words are coming out at 40 nanosecond rates, I still know this would be my first bit, second bit, third bit. So the time difference that I can do in software between the bits, because I'm not software, I mean, it doesn't have to be real time, it's MATLAB. So when I come out here, I know the distance between each one of these is 5 nanoseconds. Does everybody follow that? Okay, so I'm chunking the data out very fast, serial, save it serial and then chunk it out slow, but then I still know the bits correspond to the faster rate. So that's what's meant by serial mode. That's what's meant here by reading the data out in serial mode. Okay, you see there's a little bit of an attenuation. Well, if I'm at a high enough frequency, I know I'm going to be filtering, it's going to see a little attenuation in the signal. Okay, in parallel mode, what I'm doing is I'm summing all those bits out. So I'm effectively filtering them by adding the bits together. So instead of treating them as 8 individual bits and reading them in that way, what I'm going to do is just add the bits together. And what the problem with that is, I don't know if there's 4 ones and 4 zeros. I don't know if it's like this, if I add them all together, or like this, or like this. So I lose information. But it's easier to just add them and chunk out the smaller word. Okay, so if I add all the bits together, what is that doing? Yeah, it's doing a filter, 1 minus z to the minus 8 over 1 minus z to the minus 1. So I'm doing a little bit more filtering here than I am in the other case. And it's decimating because I'm getting them out at the slower rate. I don't know if we can see that here. Maybe not. I actually don't remember exactly what was going on in the code. All right, so this will tell you here. So if I look, this is in serial mode. If I look at the bits, they're it's hard to see here. They should look different, the bit stream, than if I look in the parallel mode where I add them all together. In fact, in the serial mode, your bits are 1s and 0s. When you add all the bits together, then you normalize by 8, you can get any value from 0 up to 8. So that's why here in parallel, when I add them together, I get values other than 0 and 1. Does everybody follow that? So that would be like, I'm going to add, if I had 8 ones, then I'd get a 5 out because I'm normalizing. If I had 7 ones, I'd get a corresponding. So if I go count the levels here, 1, 2, 3, 4, 5, 6, 7, 8. We're all added together. Does it make sense? Okay, and then again, we're going to go through this. If you look at the spectrums, here I've set my bandwidth based upon the oscillation frequency and the parameter oversampling ratio. So here's my desired tone. When you do a FFT, you get these side lobe points. So there's 2 side lobes, or a total of 5 points here. So you need to subtract those out of your spectrum when you're calculating noise and then limit your bandwidth. So just as a sanity check, why is the spectrum going up like this? Noise shaping. And then what if I increase the number of oversampling ratio? If I increase the number of points I oversample, what happens to this change from red to blue if I increase the number of points I'm averaging? Yeah, it goes, and we can rerun the sim and show that. It pushes it down. so we have a smaller bandwidth. And then a peak here, you can see how it's peaking at whatever the sampling frequency is, and this is out of band noise, which I don't use in my SNR calculation. So we'll go through this if you have questions. You can see here that the in serial mode, the SNR is 41 dB. And you can go over here, you can see in parallel mode, it's 39 dB. And then if you want, you can go look in here, and you can say, oh, for K-path OSR 64, if I go, oh, let's see what happens if I have an OSR. Got to be careful because my signal might be, let's do 128. Might be filtering out my signal if I drop the bandwidth by a factor of 2. So let's see. Oh, we still got signal. And as you might expect, what do I see? Reduction in amplitude, because now I'm averaging more points. If I go look, I should see a corresponding increase in effective number of bits. I do, and in the signal to noise ratio. Okay, one more thing. Are there any questions before this? Because this switch capacitor, you saw the projects. I want to cover one last thing. Okay, so the last thing, oops. Let's get rid of this. If you go to the course web page here, you click on errata, and you go to this. Would you post an example of a continuous time KDS? So I did with the MATLAB script. So I wanted you to look at this just real quick. And if, oops, we can just open, there's already the file in there. So let's go to desktop, continuous time, KDS. Well, you know what, we actually need to look at the schematic. So this is basically the same thing as the other topology, except in our feedback path we have a resistor. These switches here aren't for switch capacitors. They're basically, both switches have to be on in order for the resistor to be connected back to the integrator. So the clock phases here set the widths of how long those switches are on. So it sets amount of charge that you can feed back and feed into the integrator. So in the ideal case, let's say there's 8 paths. Both of these switches are on at 1/8 of the clock frequency. So they're controlled with different phases of the clock. So 1/8 of the clock frequency. So if we were running at 100 megahertz, this resistor would be connected for 1.25 1.25 nanoseconds. This one for 1. So if there is a 0 or a 1 here, it's connected and discharges or charges the capacitor there for that short period of time. So you notice now we don't have to worry about the scaling. Here, this resistor can be the same size as this one, and if the periods are 1/8, then you can get the right magnitude response. So what you have to do in your design, unless you're really circuit impaired, I don't want you using, because I did all of the components that'll get you. I mean, you don't really need to redesign them unless you want to try to improve the performance. You just need to implement transistor switches like TGs or whatever for these switches, and then see how things go. What the heck is going on here? So let me go highlight this node. No, I can't even remember what I did here. And then let me highlight. Oh, this is a continuous time second order one right out of the book like we covered last time. I'm like, there's only one feedback path. But if we go take a look, and that's one thing I would like you to look at is the performance. In the book it's 8 paths and 1 op amp. That doesn't mean that's what you have to use. You could do second order or some other topology and improve the performance and get better design, all right? I want to see that, oh, well, he did that, so I'm doing that. That's bad, okay? I want you to do it on your own, okay? So I'll just show you. If you look at that and we hit run, and you look and you say, okay, and you look, okay, that's what the output looks like, and you can say, okay, here we get almost 10 bits effective number of bits, or almost 60 dB SNR. Okay, so that's getting to be pretty significant given the effective sampling and how simple the circuit is. Does anybody have any questions? Yeah. Yep. Well, if you have the two sigmas, that's the topology here where you're looking at it. But you integrate it twice, and then the comparator though can only look at one place. So you have to make sure whatever comparator is, it's connected one place. No, you could do second order. I want you to do better than what's in chapter 9, because now you don't have the see here I'm generating my clock signals, I'm using everything's ideal. If you get to 10 bits, that's really good, because with Spice there's numerical issues, so you're getting above 10 bits will be a challenge. All right, I mean, I think you could probably play some games if you choke off the bandwidth a lot. I mean, but that's more MATLAB than anything else, because what you're doing is you're choking off the noise, okay, filtering it out and with a filter. Okay. All right, any last questions? All right, got to make sure we have time for our grade booster today. You haven't had a quiz in a long time. I know you're missing them. I know I'm missing grading them and making them up. All right. So let's go and close this. And close this. And let's talk about delta sigma modulation. I'm assuming everybody knows at this point how to implement this block, the integrator here. Oops, we need to zoom out a little bit. So let's go through and derive the transfer function for this. Now we could put it basically at the end of what we derived in chapter 5. So then what comes in here is, what do I label this signal as? Yeah, V out of Z. And then this signal is V in of Z minus V out of Z. So then I can write V out of Z is equal to VQE of Z plus Z to the minus 1 over 1 minus Z to the minus 1 times V in of Z minus V out of Z. And so if I multiply both sides, I get, yeah, we'll feel the pain. I don't know if I'll do this most of the time, but 1 minus Z to the minus 1, VQE of Z times 1 minus Z to the minus 1 plus V Z to the minus 1 Vn of Z minus Z to the minus 1 V out of Z. And so would everybody be okay if I went like this? And then I said V out of Z is equal to Vn of Z, Z to the minus 1 plus VQE of Z times 1 minus Z to the minus 1. Or VQE of F. Let me see how I wrote it in the book. Any questions about that? Okay, so tell me, how about Wenlan? Tell me, what is this? Tell me, interpret this equation. I know I'm not challenging you. What is that equation? Tell me how the output or input appears at the output. Thank you, Wenlan. Yeah, with the delay, and then the output noise is? Yeah, what happens to the quantization noise? What's the modulation noise in the output? What is it? What am I doing to the quantization noise? Differentiating. I want you to have the right lingo. You differentiate the the quantization noise. Differentiating the quantization noise is called. What is the noise called if you differentiate the quantization noise? Yeah, come on, man. All right, so there we go. That's a first order delta sigma, and you can see why it's called delta sigma. You take the difference in the sigma, okay? Uh, the implementation of that topology, if we use the basic topology that we see here, is seen right here. And so if I ask these things, should be a review and should be boring you. What do I think of this as? Yeah, it's the quantizer. It's additive noise. It's additive noise. So on Wednesday morning at 10 o'clock, Dr. Stuberud's student Kay is going to defend her dissertation, and she's doing work in delta sigma modulation. So if you can attend it, that would be really nice. I forget which room it's in. 10 o'clock on Wednesday morning. Okay, so she's going to talk about using the delta transform to model stability in continuous time delta sigmas. So it should be good times. That's another thing I did this weekend was read her dissertation. All right. So, and then this topology is a discrete analog integrator, and I want to point out one specific thing. The gain of this topology is equal to the feedback divided into the input, CI over CF. I haven't seen any flyers for it, so that's why it would be nice, because you'll see some of the stuff that she's doing, and she'll talk about a lot of the background that we've gone through. Okay, are there any questions about that? Because I want to pause and do a simple simulation, and then I want to talk about the digital one. At this point, let me just make a couple comments. So the gain here, CI over CF, is given by this times the delay. This is a delaying integrator. Okay, real briefly, if you look at this quantizer right here, if this signal is swinging small, this one always swings the same amount, right? It swings between 0 and VDD. And so if this signal's small, tell me how I could, looking at this circuit, this is something you'll need to know for your projects, if not quantitatively, qualitatively. How would I reduce the signal swing here? Tell me what I could do in the circuit. Now, what am I the king of? Trivial question. So tell me what I do in this circuit, and we'll verify it in simulation to reduce the swing here. I could adjust this capacitor. Well, either one, right? If I make this one smaller or this one bigger, then I'm going to reduce the signal swing here. Why is that important? If you do your designs and you don't design or select your capacitor values right, the integrator is going to saturate. In our analogy, what that means is the water will overflow the edges of the bucket. If the water overflows the edges of the bucket, you're no longer going to have a good conversion. So you need to make sure the bucket's big enough, given the time frame you're working at, that the water doesn't overflow. And that means you need a big enough capacitor. Okay, so everybody follow that. So that's a big deal. And we'll talk about that more later too. Integrator saturation. Okay, so let's pull up a simulation. We'll verify that. So let's go boom. Today's the 27th, so we go here. Extract here, and then let's look at figure 7.3. And we hit run. And at this point, does anybody look at this plot and get confused? Makes sense, right? Okay, so how would I convert that? Well, you know how to do it, right? 1 would be a 0, 1, and a 1, 1 0 would be a 1, 1, or a minus 1. Okay, so let's look at the output of the integrator. And you see here that it's going to 1.4 down to minus 0.4, and I look at the power supply voltage, and it's VDD, and ground. So that's not practical. Does everybody see that? So what I'm going to set, I'm going to reduce the swing. So why don't I make this, oh, how about 4? I'll go rerun the simulation, and now I'm well within the boundaries. Now we can we'll derive equations for how to govern that output swing later. But the point is now, if you look at your if you're doing your projects and you look at your integrator and it's going up to 5 volts or even close, or down to ground or even close, your integrator is saturating and you're not going to get good results. Okay. So if I go look at the output, what do you think is going to happen? Basically, look, since I'm using ideal components, it's going to look the same as what it did before. Let's change that back to 1 and see what difference. There'll be a little bit delay maybe in the pulses, but if I hit run, okay, so this gain is changing. Well, how can this gain change and the circuit behave the same? The gain of the integrator. What's compensating for changes in the gain? Yeah, the comparator. Yeah, if I reduce the signal swing here, the comparator gain is its digital output, 0 or 1, divided by the swing here. If I reduce the signal swing, the comparator gain jumps. So it keeps the forward loop gain equal to 1. Is everybody clear on that? That's one of the big reasons why they like single-bit quantizers are used, because if you have a multi-bit quantizer, if you remember, it's harder to adjust the gain. You're basically limited, okay? And just to make sure everybody follows that, go look at we'll look at the book. Let's see, where was that? In like chapter 5 maybe? Maybe it wasn't. Well, no, the problem is if you make your capacitor too big, then what happens is you choke off the bandwidth, and also you get too little of a signal to resolve for your comparator, because remember, you're using a real comparator, so if you reduce the signal levels, the comparator has a longer delay in making a decision. Yeah. Well, more filtering, and here's the plot, but you can basically imagine if you look at the slope as being the gain, you have much less variation if it's a multi-bit versus a single bit. Okay, so you have problems there. Okay, so let's go talk about digital modulator. Are there any questions on that? Okay, so the digital modulator is seen right here. And you can also do delta sigma modulation using digital techniques. And if you look at the digital techniques here, you might ask, why would I want to do that? So let me qualitatively go through this. Oops, I've got 2 2s here. So okay, so first off, this is the same block diagram we had for the analog case, right? This is an accumulator. What's another name for an accumulator? Integrator. It's a delaying integrator. So I use that in digital techniques. Here it is. So then I've got a word that's coming in here that's some number of bits. So say it's 10 bits. Just like I have an analog signal, it's just continuous time coming into the analog modulator. Okay, so then I come into my accumulator, and out here I look at, this is adding up, this is integrating. Out here I look at the MSB alone, and I output 1 bit, 1 0. So if my digital code, was doing this, whatever, then I would have exactly the same thing I had before, except that I had with the analog would be a 1-bit representation. When I'm up here, I'd have lots of 1s, and when I'm down here, I'd have lots of 0s. So here's my quantizer. It's a simple mux. I feed back, oh, what is this number? What is 0, 1, 1, 1, 1, 1? What is that in decimal? 2's complement. No, decimal 2's complement. Yeah, VDD, sorry. Yeah, it's VDD, or VREF I was looking for. Okay, and then what is this 1, 0, 0, 0? Ground, or VREF minus, right? So I'm feeding back either VDD or ground. Does everybody see that? Back to the input and subtracting it. So it's exactly the same thing as what I had before. So now the question is, does everybody understand this signal here is going to be clocked at a different rate? I mean, the overall clocking of the DAC or whatever is generating this will be slower than the rate at which I clock this circuit. Does everybody follow that? So here I might have a clock rate of a megahertz. Here I might have a clock rate of 100 megahertz. And so this has to be at a much faster rate. And the benefit here is that I take this digital 10-bit waveform and I represent it as a 1-bit code that comes out at a lot faster rate. The benefit of the analog is I got an analog signal and I get a 1-bit code that comes out digital. Here I'm saying digital on both ends, but my bit stream comes out very fast relative to this one. Any questions? I'm assuming everybody can make the transition. 1 bit, easy to transmit. 10 bits, less easy. To keep the information, I got to go faster here. This has to be slower, so I get oversampling. And just to be complete, let's go ahead and define that one more time. The oversampling ratio is defined as the clock frequency, or the sampling rate, divided by 2 times my bandwidth of interest. Okay, so if my bandwidth of interest was 1 megahertz, my sampling rate was 100 megahertz, and my oversampling ratio would be 50. Does everybody follow that? And we'll talk again more about that. Okay, so if I wanted to get back, thank you. If I wanted to get back the signal, what would I do from this 1-bit code? Let's do it 2 ways. Let's say this is an analog signal, comes to a DAC, goes in here. What if I wanted to reconstruct the analog circuit coming out of this 1-bit code? What would I do? Well, remember, it's a 1-bit code. How do I cheat in my simulation so I don't have big digital filters? Yeah, I use a filter. So I use a filter and then it averages. As we just saw, you can average that and then you get an analog, and the better you average, the more it resumes. So everybody follow. The whole point here is I don't want you to think that sigma delta is just for analog to digital conversion. You can also use it for transmitting data. Questions? All right, so assume that makes sense. Okay, so let's look at the modulation noise, and let's take our basic equation. This is another good quiz question. So we had VQ, or V in of Z is equal to, or I'm sorry, V out is equal to V in times Z to the minus 1 plus VQE times 1 minus Z to the minus 1. Here's where I'm like forest for the trees. Write this equation in the time domain. I'll start you out. V out of NTS equals all right, nobody was challenged by that. Good. Oops. Is everybody cool with that? Okay, so if I want to look at the modulation noise, I'm going to take the noise transfer function and multiply it times what? VQE. And the noise transfer function for this first order modulator is, let's do it in 2 different steps. 1 minus Z to the minus 1 times VQE, but we'll write it as 1 minus E to the minus J 2 pi F times what? DS, right? Or divided by F sub F times VQE of F. So if you come and watch her defense on Wednesday morning, you'll see she'll probably talk about this. What is VQE of F? Oops. Yeah, it's VLSB. Well, let's do voltage spectral density. VLSB over. Is that it? And what's the assumption there? So everybody, all the noise is there, just out of sanity. What does that integrate to? If we integrate for the VLSB, well, wait, it's not a probability density function. It integrates to what? Whoops, the RMS value. Yeah, but what is VQE RMS? Yeah, I'm just repeating myself. You can see the assumptions that are made. Yeah, try to go to the dissertation because students love it when there's a lot of people attending their defense. Evil chuckle. All right, so if we integrate that, we'll get, I'll just show you the equation. Yeah, I'll write it down here. This is equation 7.8 on page 237. Okay, and so let's go ahead and simulate that just to see what the spectrum looks like. And we just showed you in MATLAB what it looks like. And again, I'm going to show you a smooth spectrum, but it's in real life. This is just plotting. I could have plotted it in MATLAB as well. In real life, as you've seen, it's not a smooth spectrum. So there you go. So where does, just looking at this, where does the peak occur? What? Yeah, but what I mean, what's the significance? What is it? Yeah, FS over 2. And if I'm doing noise shaping, where's my signal spectrum of interest? Yeah, down here, right? So I pass this spectrum through a low pass filter. So just if I had a sinusoid at 2 megahertz, how would I modify this? This is my input signal. How would I modify this? This is my spectrum of my modulation noise. If I have an input sine wave at 2 megahertz, tell me how to show that in the spectrum. Yeah, an impulse right here at 2 megahertz sticking up, right? Boom, there it is. Easy. I'm asking trivia. I didn't understand that class, man. All he did was math. All right. I understood buckets and water, and that was about it. Okay, so let's talk about estimating the RMS modulation noise. So this is 2.37. And I'm going to do this in 2 different ways. What I'm going to do here is I'm going to assume a bandwidth B, and then I'm going to calculate the noise in the bandwidth B, assuming a brick wall filter. So the filter comes over, comes down, boom, no sink filter. Then I'm going to go through and do it with a sink filter. If you look at those scripts, there's actually code in there to implement sink filters if you want to see what it would be like if you were doing that in a real circuit. So does everybody follow that? Just a bandwidth B and then block wall. Okay, so we can write that then, that modulation noise VQ, or the RMS noise, is, pull everything out twice because I'm using a one-sided spectrum, VLSB squared all over 12 FS, which is VQE, times 4, pull the 4 out, which was from our little 4 here. And then we're going to integrate from 0 to B. And that's sine squared of pi f over fs df. Okay, so I'm going to just write the result down. Oh, So here we're assuming this is what I talked about a moment ago. The band, I'm going to write a little bit different. The oversampling ratio K Okay, so this is confusing. In your projects, there's going to be two Ks. One is going to be the number of points related to your bandwidth, but then you're also going to have a K which is related to the number of paths that you feed back. Okay, so there's two different Ks. They behave the same. That's why the same value is used. But for now, we're not going to talk about K delta 1 sigma. So this is my oversampling ratio, and I already went through this, but I called it OSR a moment ago, and that's equal to my sampling frequency divided by 2 times my bandwidth. Or in the book, its bandwidth is equal to Fs over 2K. So if I increase my oversampling ratio, that means I'm going to do what to the bandwidth? It's going to shrink, right? And so then if I increase my oversampling ratio, I'm going to get less noise and a higher signal-to-noise ratio. Yay? Okay. So if you go through and you use a value here that you assume that F over Fs is much, much less than 1, so it's large oversampling ratios, then you can say sine x is approximately x, and you can derive the VQE RMS, it's on page 238, as approximately VLSB all over root 12 times pi over root 3 times 1 over k to the 3/2. Just intuitively, do I see with this equation that if I increase the oversampling ratio k, that my VQE RMS is going to shrink? Yeah, does everybody see that? So now, more importantly, if I look, I'll just put the book up there for this. If I look at what happens, and again, hopefully she'll cover some of this in her dissertation defense, because it's background stuff. If I look at this, and I ask, well, what happens? I get 30 log of k. So what that means is, for every doubling in k, I get 1.5 bits increase in resolution, or 9 dB increase in SNR. Okay, so that's pretty significant. Remember, does anybody recall what we got with simple oversampling? Yeah, 0.5 bits for every doubling, or how many dB is that? Yeah, 6 dB in SNR increase. Okay, does everybody follow that? Okay, so just as a trivial question, because I want to make sure no one's daydreaming about dinner or something like that. If I were to ask you what's the equivalent equation for this for just a regular Nyquist rate data converter, what would you say? How do I modify this equation for a Nyquist rate data converter? Get rid of this stuff. That's why I wrote it like that. So the Nyquist is 6.02n minus plus 1.76. Here I got to get rid of the secondary terms for oversampling. So you can see that G if k was 2 or 4, there may not really be, I think 4 works out. There's no benefit of using oversampling. It's only when you start getting above 4 that you start to realize a benefit. Any questions? And then comparing the first order noise shaping to simple oversampling, you see here, if you can oversample 1,000 points, you can get a really high increase. So I have not funny, but I have a story about this. So you know flash memory? Did I tell you this story? So back in the mid-2000s or whatever, flash memory was really taking off, as before they had the thumb drives and all that. So I developed these techniques for doing delta sigma modulation for sensing flash memory. So nowadays, I haven't told you this? Okay, nowadays, well, and it's been like this forever, they basically charge the bit line and then they turn the flash cell on, and then how long it takes the flash cell to discharge the bit line corresponds to the data value. Okay, so what I said was, well, it'd be great if you could sense indefinitely and use delta sigma techniques. Okay, so in 2007, 2008, the economy was really crappy, all right, and companies were going out of business and all that. So I was doing consulting at Micron, and they said, well, let's build it. And so we built it, and I was able, using this simple technique, to basically sense 1 picoamp of current change in the cell. So I could do an IV plot of each memory cell, and then I was like, man, we're going to shoot the density of flash through the, maybe I should go offline for this, through the roof, all right? And so I went in with all the VPs and all that, and at that time they were trying to keep the doors open because the economy was really bad, and so companies were dying, like I said. And we went in and said, that's great, and can I put a test chip on one of the radicals, and can we build this? And they go, well, this is great, and we like it, but nobody else is doing it, and the market conditions now are such that we don't want to take any chances whatsoever, so they didn't do it. But I got a ton of patents out of that, so it just tells you. Maybe someday you'll see that come into play again, but it's very simple to implement because you need basically your bit line is a big capacitor, and then your memory cell is a current being pulled out, and so your delta sigma is just like a D flip-flop in a feedback path to keep the bit line at a constant potential, or to add the water back in. So if you average 10,000 points and your feedback current is like a microamp, well, now you're at like 10 or 100 nanoamps, and you can even sense longer because the sense can be indefinite, so you can really shoot up the signal to noise ratio, average out noise and mistakes and all that. Okay, so let's talk about decimating the output of the noise shaping modulator. All right, and you might think, well, doesn't it take a long time? Well, because of the time constants involved in flash, it takes microseconds anyway. So if you're running at 100 megahertz, you have plenty of time to do delta sigma. You don't have a problem with. Yeah, so I'm going to do a PowerPoint on this just to show you what's going on. So I know you hate PowerPoint, but I do not want to keep covering less than what I said I would. You don't hate PowerPoint? Oh, that's good to know. You love PowerPoint? All right, so here's my SNR ideal. So I'm going to change this variable here, n, to n increase, to increase for the given oversampling ratio k. So I come over here, we'll be able to go real fast with PowerPoint, man. Hold on. When I increase, I solve for n increase, and I get this equation here. Okay, so basically what this says is, given the number of samples that I'm averaging, or k, so the oversample ratio, the k over fs times 2 times the bandwidth. Okay, if I go back, and we could actually do MATLAB scripts and change the oversampling ratio, and you could see that you'll get to the point where you won't have the signal anymore in the MATLAB output because it'll get filtered out. I can solve for n increase. Well, if that was 4 bits, then I know the output of my averaging filters have to be at least 4 bits wide, right? So what I'm going to do to calculate how many sections of sync averaging filters I need is I'm going to take that number and say that the output, what is log base 2 of k, is the number of bits each sync filter increases as you go from the input to the output, right? So if it's a 1 minus z to the minus 8 over 1 minus z, I'm averaging 8 points. So k is 8, so log 2 of 8 is 3. So if I had 4 bits, then 1 sync filter wouldn't be enough to capture the resolution, and I'd need 2. Does everybody follow that? So L would be 2. And the way it works out is that the order of the sync filter has to be equal to the order of the modulator plus 1. Okay, so let's go throw some numbers in, all right? Just to make sure it's clear. How was that? Too much PowerPoint. Now back on the pencil and paper here. Okay, so let's say that we have a sampling frequency of 100 megahertz. And let's say we need a bandwidth B of 6.25 megahertz. So then I ask, all right, what is K? And K is my oversampling ratio. And that's equal to 100 megahertz all over 2 times 6.25, which is 8, yeah. So I need, my filter on the output is a 1 minus z to the minus 8 over 1 minus z to the minus 1, but I need 2 of them for a first order. So for first order, M equals 1, and then my filter is L equal 2. So everybody follow that. So let's go through. So I've got my clock coming into my first order modulator. Fs equal to 100 megahertz. Then here I have how many bits coming out of the modulator? 1. Okay. This stuff's hard, man. Then I go to one filter here, which is 1 minus z to the minus 8 over 1 minus z to the minus 1. And then you know from filter design, this one, you increase the word size by, for this filter. Wait, how much do you increase it for the comb filter, the 1 minus z to the minus 8? That's 1 bit. And then to make the integrator, right, we need 2 more bits. So we get how many coming out? 4. And then we go over here and we say, okay, I got another one of these filters. And then how many do I have coming out of there? 7. Does everybody follow that? So now I say, okay, well, let's go back and check that equation because it's got to be greater than. So if my equation comes out to 6, 7's greater than 6, that's fine. But my equation says that my increase is 30 log of k minus 5.17 over 6.02. So I go back and I say, n increase is equal to 30 log of 2 to the 3 minus 5.717 all over 6.02. So what is 30 log of 2? What's log of 2? Remember, that's a common log. I thought it was 0.7. I'm saying it's not common. What am I thinking? I'm crazy. Log, oh, 0.3, you're right. Okay. I should know that for 3 dB. All right. It's funny, I find myself saying more often, I used to know that. So that's 0.3. So 0.3 times 90 is 27 minus 5.17 is 22. 22 divided by 6 is 4.3, right? So I had 1 bit coming in. Now I have 5.3 effective. Is that correct? Could I have gotten away with 1 filter? Nope. So that's why I have the 2 filters. So I have 7, that's more. Now the lower bits, they're not going to be that significant. They're going to be a little bit noisy because, you know, I'm only getting an increase effectively of 4 bits and I'm getting an output of 7, but that's fine. Any questions? So the key point here is that L is equal to M plus 1. Your filter is going to be 1 order greater, and that's, you're going to see that's the same on a second order modulator too. You'll need 3 sync filters for a second order modulator to filter to get the right number of bits out. All right. How are we doing on time? You know what? I think I'm going to punt on having the quiz today. 27th. Decimating and... Oh, no, I'm not. We're right on time, man. This is where we're supposed to stop. And then we pick up with pattern noise from DC inputs when we come back. Oh, but I do want to cover one last comment on one last thing. You remember how when we calculated the quantization noise, the RMS value, I said we'll do a brick wall filter from 0 to B? Now we're going to use a sync filter, the second order. I just want to briefly go through that. So if you look at the following equation, now instead of using a block filter with a bandwidth B, we're using a real sync filter, and this one obviously is the sync response squared. So it's the 4th to the 4th power. And you see I'm going to integrate this. Now, what's going to happen is you're going to see that, hey, using the sync filter, I actually get better signal to noise ratio than what I got with the block wall filter. Well, of course, that's wrong. If you look at this, you say, well, gee, I'm not removing the noise from all the, because I've got the noise here, my filter's not removing the higher frequency noise like I did with the ideal block wall filter. So why would this equation say that the signal to noise ratio is better? Well, what's not taken into account here, and it's discussed here, is that you're also going to reduce the signal level, and that's not seen in the equation. So it's actually worse to use a sync response filter than a block wall filter with a bandwidth B. Okay, does everybody follow that? So just to be complete, this is what I got. Basically the same results apply. It says comparing the SNR, we see that using a sync filter results in only over the ideal filter. If we remember an increase over the ideal filter, which makes no sense. However, remember that using a sync filter results in a droop in the desired signal. So you reduce the desired signal. We're not putting that in the equation for SNR. That causes your signal to noise ratio to drop. But we still use the results. Any questions? All right, let's stop here.